Okay, good morning, guys. Assalamu alaikum. Welcome back to grade 11 physics by Inspired Teens. In today's lesson, we are going to be doing electromagnetism. Okay, so sorry for all the delays and for all the technical issues, but yeah, just load shedding and it's causing a whole bunch of complications. But nevertheless, let us continue. And of course, we're probably going to end slightly late. Okay, so firstly, electromagnetism. Okay. We are firstly going to talk about the induction of a magnetic field. Okay, so it says when current passes through a conductor, a magnetic field is induced around a wire. Okay, so this is through any conductor. If there's current that's passing through it, a magnetic field is created around it, right? So just give me 1 second. 1 second, I'll be back shortly. Okay, cool. Okay, so that's what you should keep in mind, right? So any circuit, right? Circuits that we've done in electricity, any circuit or any conductor, any wire, where current is passing through, you should understand that a magnetic field is always created around that conductor, okay, around that wire. Okay, then it says the direction of the magnetic field can be determined by the right-hand thumb rule. For straight single wire, point the thumb of your right hand in the direction of the conventional current, and your curled fingers will point in the direction of magnetic field around the wire. So here we are talking about what type of direction? Either clockwise, okay, or anti-clockwise. Okay, so let's have a look at this example. Okay, so yes, right hand rule. So we've got to use our right hand. If you use your left hand, you're going to get the opposite, which is going to be the incorrect answer. So when we use our right hand, okay, and we consider this, so you should always remember out of the page and into the page are represented by the following diagram. So out of the page can be represented by a dot. So what we have here is basically the current carrying conductor. Okay, the current carrying conductor is basically the wire represented by the circle. And if there's a dot in the middle, that means that it's coming out of the page, and I'll explain that in a bit. And then here is the current carrying conductor, and we have an X that's into the page. Okay, so basically the reason they say page is because they like trying to get you to understand it, right? If you had a book and you would consider, like, if there's a page in front of you going into the page, so basically into the page means away from you, going away. I'm just gonna say, okay, I'll say away from you. Okay, and then out of the page is coming towards you. Okay, so coming towards you. So if you have to have a page in front of you, like a flat page, okay, like this, just in front of you. Okay, if you've had to add a flat page in front of you, coming out of the page means coming towards you, and going into the page means going away from you, right? Like directly towards you. Okay, so that's what we consider when we say out of the page and into the page. Then we use our right hand, and our thumb, the direction of our thumb should be represented by the direction of the current. So basically you need to take your thumb, so you have your hand, in this right hand rule for induction of magnetic field, we're only using two things on our right hand. The first is our thumb, and then the rest of our fingers are just considered as one. Okay, so two directions we are determining. One is our thumb, and the other is the rest of our fingers. So if I had to point towards myself, okay, so out of the page, I'm doing the first one. I have to point my thumb towards myself. Okay, if you take your thumb and you point your right hand thumb and you point it towards yourself, you curl the rest of your fingers. If you curl the rest of your fingers like downwards, you will see that your fingers are pointing in an anti-clockwise direction. And that's represented here. Okay, so you should be able to identify when you do it personally, you take your right hand, okay, and you point it towards yourself, and then you curl your fingers, that this is true. Out of the page, you will see that your fingers are pointing in this direction, anti-clockwise direction. Okay, if that's not true, then let me know, because if you've tried it and it's not in the same direction, then there's something wrong. Now, what about out of the page? So you take your right thumb, your right hand, you point your thumb away from you, and you curl the rest of your fingers. You will automatically see that your fingers are now pointing in a clockwise direction, which is represented by this diagram. Okay, so this diagram is in the clockwise direction. Okay, so here's another example. If we're not considering into the page, okay, if you just had to turn any direction, okay, you consider a cable or a wire, a current carrying conductor, to be more specific. If, as long as you know the direction of current and your hand, okay, you take your right hand and your thumb is pointing in the direction of current, you would be able to determine the direction of the magnetic field that is created around this conductor. So if you have to do the same thing with your right hand and point your thumb up, you would notice that when you curl your fingers, they would point in a anti-clockwise direction, and this is it here, represented there. Okay, B is magnetic field and I is current. Okay, so that's what's represented in this diagram. For a wire loop, okay, the magnetic field is the sum of the individual magnetic fields around a single wire at each end. Use the right-hand rule for a single wire at each end of the loop. One second, it's out of the page, it's out of the page. Okay, yes, so basically, in this case, when we have a loop, okay, at each end of the loop, okay, what you're going to consider is, into the page, okay? So what you're going to consider is the end of the loop. So here is the end of the loop. And here, sorry, here's the end of the loop here and the end of the loop there. Okay, so this is just a constant wire. So instead of determining it for a single current carrying conductor, here we are basically going to use each end, because it's like a circuit basically. Okay, so it's as if you would have to put a page here. Okay, and in this case, current is traveling in this direction, so it's traveling in this direction, in this direction, in this direction, going around, coming out of the page eventually and traveling in that direction. Okay, so it's like you can use a page, but also it's you consider current. Okay, you need to consider the direction of current. So in this case, as you can see, when it enters, the current is away from you, so you're going to use your right hand, point away from you, and you will see and you will see that this holds true. Just one second. Coming out the page. Okay, so so in this specific case, you will see it going into the page. Okay, because again, you're not like you have to consider into the page, right? You basically are considering the right hand rule once again, where you are pointing your thumb of your right hand in the direction of current, and that is going to help you to determine the direction of the magnetic fields around each loop. Okay, so that's basically what this is explaining. Okay, so you would do the same thing here, and you would do the same thing there. You consider the direction of current. Okay, you consider the direction of current, and you use the right hand rule along the way each time. So here you can see that the direction of current for when it starts the loop to when it ends the loop is the same, and the reason for that. Okay, because again, it follows the direction of current, just like in electricity. Okay, what about for a solenoid? Okay, so for a solenoid is basically a coil of wire. Okay, I'm sure maybe some of you have done an experiment in lower grades, or maybe some of you have even maybe you've seen a solenoid, right? A lot of the times you use a bolt and then you wrap the current carrying conductor around the bolt. Okay, that forms a solenoid. But basically it says, for a solenoid, curl your fingers around the solenoid in the direction of conventional current, and your thumb will point in the direction of induced north pole. This is known as the right-hand solenoid rule. So this, so it works vice versa as well, meaning if you have the direction of current, you know the direction of the north pole. If you know the direction of the north pole, you have the direction of current. Okay, so this one can actually get a bit tricky to understand in which direction your current is moving in, but we can go through it. So let's have a look at this solenoid, right? Okay, so normally what would happen is maybe perhaps they'd give you the direction of current, or they'd give you the direction of north pole. So let's just say that the north pole is this direction. Okay, and in that specific case, right, induced north pole is in this direction. So basically, right, when we have a current carrying conductor coiled up into a solenoid. Okay, that's exactly what we have now. Oops. Okay, we have a current carrying conductor coiled up into a solenoid. Now, due to this, if there is current, okay, so in this case, I think the current is traveling in this direction. Okay, if there is current that is flowing through this solenoid, if there is current that's flowing through this, through these wires, okay, there is going to be there's obviously going to be a magnetic field from the first thing that we learned, that as long as there's current flowing through a circuit or through a conductor, it will induce a magnetic field. Okay, so what happens here is this entire solenoid is going to induce a magnetic field around it. Okay, and it will induce a north pole and it will induce a south pole. Okay, whichever direction it is in. Okay, because it's a magnetic field. Okay, so that's what occurs when current travels through a solenoid. Okay, so in this specific case, right, again, the way you would curl your fingers would indicate to you the direction of north pole. So again, so in this case now, you're either going to curl your fingers depending on the direction of the solenoid, of course, but for this specific example, you're going to point your thumb in the right direction or point your thumb in the left direction. Okay, so if you know the current, then of course you're going to curl your fingers towards you, or you're going to curl your fingers away from you. So in this specific case, they give the direction of current. Okay, so current is coming in here, going around, up and around, and up and around, and up and around, until eventually you see it gets here, and then comes around and goes over and ends there. Okay, so in this specific case, right, we choose a single loop to help us to determine the direction of current. So you will see in all of the loops, right, the current is going this direction. Okay, it's going down at the back and coming up around at the front. Down at the back. Okay, here at the back, down, 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 and up and around in the front. Okay, down at the back and up and around in the front. So in that case, we're curling our fingers always away from us, because if you notice with your fingers, you'll see that when you put your fingers as if it was at the back of the solenoid, your fingers would point down. However, when you bring your fingers back up, when you curl your fingers basically towards you at the front, if you were working at the front, okay, you would notice that your fingers would point in the upward direction. Okay, so that entire motion of your fingers throughout that entire, whether you're at the back going down or whether you're in the front going up, your thumb is pointing towards your left. Okay, and it might look flipped in the camera, but do it with your own finger, with your own hand, right? So in that case, that's how you would determine firstly, the direction of north or south induced pole of a solenoid, as well as perhaps the direction of current, or vice versa, right? If they give you current, you can get the direction of the magnetic fields, or if they give you the direction, if they give you where the induced north pole is or where the induced south pole is, you can get the direction of current. Okay, we'll do them in examples as well so they make more sense. Okay, let's have a look at this. Induction of an electric current. Okay, so here we said, firstly, we learned about induction of a magnetic field. Induction is basically like the creation of a magnetic field, or something starts up because of another thing. okay? And in this case, the induction of a magnetic field means that a magnetic field is created due to something else, okay? So let's look at the induction of an electric current. So when a magnet is brought up close, so again, we learned induction of a magnetic field. That is when current passes through a conductor, a magnetic field is induced around it, okay? But now let's look at how an electric current is induced, okay? So when a magnet is brought close to a metal wire, it causes movement of charge in the wire. As a result, an EMF is induced in the wire. Only a change in magnetic flux will induce current. So basically what is happening here is now, how do we induce an electric current? When we bring a magnetic field towards it, because a magnet is brought close to a metal wire, it causes movement of charge in the wire, which is current. As a result, an EMF is induced in the wire. Only change in magnetic flux will induce a current. Okay, Faraday's law states that magnetic, okay, we'll go through this. Okay, let's read and then I'll explain it practically for you guys to understand. Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux linkage. Okay, magnetic flux linkage is the product. Okay, we'll come back to that and then they're discussing the formulas. Okay, so basically, let us just use this this little diagram. Okay, let's just use this little diagram just to help us understand. Ignore this north and south pole thing for now. Okay, but basically what happens is, as you can see, we have this wire that has no current. Okay, so before the magnet even existed, we can get rid of the magnet for now. Before this magnet even existed, okay, we just have this solenoid basically, and there's no current passing through the solenoid. Okay, it's just a solenoid, it's just conductive material like a copper or any type of wire wrapped around this, whatever the cylinder is. Okay, and then what happens is, if we bring a magnet close to it, okay, if we bring a magnet towards it, okay, what happens is current is created. Okay, but one thing you need to understand, if I have a magnet, okay, so again, we have this current carrying conductor, just, or not actually non-current carrying conductor, just a conductor wrapped around the solenoid, just chilling there. Okay, it has no current passing through it. But now if I want current to start passing through it, okay, what I should do is I should pass a magnet through it. Okay, so once I introduce, because there's no current in this wire, once I introduce a magnetic field, okay, that's when EMF can be induced. Okay, so what we need to note is we have a solenoid and a magnet that passes through it. Okay, a magnet that passes through it, but only a change in magnetic flux creates current. This is important. Okay. Let's define magnetic flux. Okay, so magnetic flux is basically do they have a definition here? Okay, I'm just going to give a loose definition, and I'm going to say number of magnetic field lines that touch the area of wire, basically. Okay, so let's just say we have an entire solenoid. Okay, or let's just say we have a square cross-sectional area. Okay, we have a square, and this square is wire. Okay, let's just say then we have a bar magnet. I think it's always north to south, south to north, no, north to south. So just say we have our magnetic field lines around this bar magnet, whatever they are, and basically the amount of field lines that touch this wire, okay, that is what we refer to as the magnetic flux or magnetic flux linkage. Okay, so again, these magnetic field lines, okay, if we do it in terms of this example, let's look at this. right? As you can see, B, again, B represents magnetic field strength. So all these lines that are coming in, these lines are the lines of the magnetic field, okay? So here we have a square of a cross-sectional area of the square of the conductor. Here perhaps we have a cylinder which represents a wire, okay? And magnetic flux is basically, just a loose definition, the amount of magnetic field lines that touch this cross-sectional area of the conductor, okay? So basically, yeah, like in a solenoid, how many magnetic field lines are actually crossing and touching the solenoid, okay? Because maybe there's magnetic field lines here that don't even touch the cross-sectional area, okay? And these would not be included in the linkage. Okay, let's maybe get this a different color. Oops. Okay, so as you can see, like for example, these two, right? These two do not, these two red ones do not touch. They perhaps magnetic field lines of the same magnet, but they do not touch what? They do not touch the cross-sectional area of the conductor. Okay. Okay, and since they do not touch the cross-sectional area of the conductor, they're not part of the magnetic flux. Okay, so what gives us magnetic flux? Magnetic flux we get from the amount of lines that actually touch the cross-sectional area of the conductor. Okay, so I hope that makes sense. Okay, so let's read this again. It says, when a magnet is brought close to a metal wire, it causes movement of charge in the wire. As a result, an EMF is induced. Now we need to talk about only change in magnetic flux creates a current. So basically, if we have to have a magnet just like this, okay, so now we understand what magnetic flux linkage is. So you can imagine that this magnet is already halfway through the solenoid. So there's so many magnetic field lines from this magnet that are touching the wire. Okay, there's so many that are touching the cross-sectional area of this conductor. Okay, so clearly there is an existence of magnetic flux, right? Compared to, let's just say, if we had to have a solenoid. Okay, if we had to have a solenoid here, just say, I don't know what's the best way to draw a solenoid. Okay, and then we have a magnet like very far, like extremely far away. Okay, then the magnetic field lines of this magnet are not going to touch this. Maybe the magnetic field lines are just here. That's it. Okay, I'm not drawing them perfectly, but perhaps the magnetic field lines extend up until there. Okay, and we have the solenoid here. Here, the magnetic field lines are not even touching the solenoid. And in that case, we would have no flux linkage, no magnetic flux, because there's no part of this magnetic field lines that cross this the area of the conductor, which in this case is the solenoid. Okay, so I hope that makes sense. Now we know the difference between when there is magnetic flux, when there's no magnetic flux. So in this case, there's no magnetic flux. But in a case here, where the magnet is extremely, like literally halfway through the solenoid, there is definitely a magnetic flux. Okay, magnetic flux linkage, because the magnetic field lines are crossing the area of the conductor. Okay, so now in this case, so that's one thing. However, in order to induce an EMF, because Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux. So the thing we learned here is when a magnet is brought close to the metal wire, an EMF is induced. Okay, when a magnet is brought close to a wire, an EMF is induced. So again, the first thing we learned was when we have current, okay, it creates a magnetic field around it. Now we learning when we don't have current, if we bring a magnetic field close to it, it will create current. Okay, it will create current. That's basically what we're learning. When we don't have current in a wire, if we have to bring a magnetic field close to it, it will create current. Okay, but it's not just enough to just leave it nearby. So let's just say this was stationary. Let's just say this magnet was chilling here. V is equal to 0. It's just stationary. No current would be induced. Okay, it is not enough to just have it there. It needs to be constantly moving. You need to have that magnet moving constantly in and out, back and forth. Okay, so the magnet has to be moving. Okay, the magnet has to be moving in and out. Okay, that's normally what would happen. The magnet would be moving inside and outside. Okay, you have to create what? A change in magnetic flux. Okay, so remember we said magnetic flux linkage is the amount of magnetic field lines that cross the area of the conductor. Okay, so in this case, let's just define it in terms of the solenoid. The magnetic field, the magnetic flux in this specific case is the amount of magnetic field lines that cross the solenoid. Okay, so change in magnetic flux would mean that there's a constant change in the number of magnetic field lines that are touching the solenoid. How would you create a change in the number of field lines that are touching the solenoid? You would move the magnet. Okay, so when we move this magnet, this bar magnet, when we move it in and out, of course, when it's inside the solenoid, that's when the most amount of magnetic field lines are going to touch. But let's just say we move it out. Just say it moves all the way out here. Okay, the magnet is moved all the way out here. Maybe perhaps then none of the lines are touching, or very few of the lines are touching. But that's actually what we want. We want a change in magnetic flux. We want it to constantly be changing. So how do you change it constantly? Again, you move it. Okay, when you move this magnet, you create a change in magnetic flux. Okay, so I hope that makes sense. What actually induces that EMF is the change in magnetic flux. Again, magnetic flux is the amount of magnetic field lines that touch the area of the conductor. In this case, it's like a solenoid. Okay, and that's what magnetic flux is. And how do we induce an EMF, or how do we induce a current, okay, on this conductor? Is by changing that magnetic flux, constantly just changing it. Okay, so now let's read it and let's see if things make more sense. It says here, okay, when a bar magnet is brought close to a metal wire, it causes movement of charge in the wire. As a result, an EMF is induced in the wire. Okay, only a change in magnetic flux will induce current. So again, only when we're moving the magnet, it will induce current. Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux linkage. So basically, the speed at which Faraday's law tells us that the EMF induced, okay, so how much voltage you want to produce is going to be directly linked to how fast you move the magnet. So the faster you move the magnet in and out between the solenoid, okay, the faster, move it fast and faster and faster, the more EMF you're going to produce. Okay, and you can obviously guess that when the magnetic field is constant, or sorry, when the magnetic field is not moving, when the bar magnet is just still, no EMF is induced, nothing. If you go just, even though there's magnetic flux, you're still not going to have EMF. So if you have a bar magnet that's just chilling inside a solenoid, not moving, yes, there's magnetic flux, meaning they are magnetic field lines that are crossing, that are touching the, what you call it, the area of the solenoid. But because it's not moving, there's no change in magnetic flux, okay? Because of that, there's not going to be an EMF produced. And basically, then the faster we change the magnetic flux, meaning the faster we move the magnet, the more voltage we are going to induce, okay? Cool, then we have magnetic flux linkage is the product of the number of turns on the coil and the flux through the coil. Okay, we'll go through. There's a definition. There's a formula for that. Okay. Okay, then we have, okay, let's have a look at this formula. This formula tells us, okay, E, which is EMF, number of turns or winding, we have E, then we have N, which is the number of turns or windings in the coil, or number of turns or number of loops of the coil. Okay. Delta, we call this phi. This is one of the Greek letters. It is pronounced as phi, as in phi. Okay, so delta phi is change in magnetic flux. Okay, and delta T is change in time in seconds in voltage. This is, I forget exactly. We'll just call it WB for now. Like Weber or something. But yeah, WB. Okay, and then in seconds. Okay, so let's have a look at it in the formula. EMF, the EMF induced, this is the EMF that we're trying to create, okay, is equal to negative N. N is the number of coils, okay, delta phi, meaning the change in magnetic flux, not just flux, okay, the change in magnetic flux. Because remember, in order to induce an EMF, you have to have a change in magnetic flux. You cannot just have flux, magnetic flux, okay, and then divided by delta T, which is the time, which is the time, basically. Okay. Okay, then let's move on. Then it says the magnetic flux is a result of the product of the perpendicular component, magnetic flux, of the perpendicular component of the magnetic field and the cross-sectional area of the field lines passing through it. So let's go through that in the definition. I mean, in the formula, this is magnetic flux. Again, this is not changing magnetic flux, but this is just calculating the magnetic flux at a certain point. It's equal to B, which is the perpendicular component of the magnetic field. That's B. Okay. Okay. Magnetic flux density. Excuse me. Magnetic flux density. I think, okay, that's fine. Then we have A, which is the area in meters. Area in meters. What area are we talking about? We're talking about the cross-sectional area of the actual conductor, or like in this case, maybe it's the wire. Okay. And then theta is the angle between the magnetic field line and the normal line. Okay, so that's important. We'll go through it in a second and we'll discuss this normal line thing. Okay, so let's just have a look at, okay, so I'm going to draw a 3D version of this and then a 2D version of it. So this is like, let's just say this is like this, exactly like this. Okay, like a coil. Okay, like a loop of conductive material, or like a loop of wire, basically. Okay. Now I'm going to draw the front view of this wire. It's going to basically just look something like this. Okay. Now, what the normal line is basically, we don't even have to utilize that. Okay, if I draw these dotted lines, what the normal line is, okay, it's a line that is perpendicular to the surface. A line that's perpendicular to the surface. So the normal line from the front view would look something like this. Okay, so that's the normal line. Just keep that in mind. Okay. Now, that's the normal line. Okay. It's perpendicular. So when the theta that we consider in this formula is the angle between the normal line and the magnetic field lines. Okay. So let's consider in this example, for instance. Okay. So this, by the way, this example is very similar to this. Okay, so here we have, the reason they've drawn it angled, it's not really skew. It's not like really at a certain angle. This is completely flat. Okay, this is as if it's flat on a table, this diagram. It's just drawn at an angle so that we can see it, because again, if it is drawn flat, all we would see is this. Okay, a very weird angle. So the normal line here is actually 90 degrees to the surface. Well, let's do it. Instead of that direction, let's do it this direction. The normal line here is 90 degrees to the surface. Okay. And the two directions that we compare again is the direction between magnetic field line and the normal line. So the normal line direction I've determined, it's vertical. Okay, that's the normal line. Magnetic field line is given here. It's always from north to south. So the direction of the magnetic field line is from left to right. Okay, and now you can see that the angle between the normal and the magnetic field lines, that angle is 90 degrees. Okay, the angle between the normal and the magnetic field line, that angle is 90. So that's the angle we consider. Okay, what about in this case here? So in this case here, again, it's drawn skewed just so that we can see it easily, but it's as if now this thing rotated 90 degrees. This guy rotated 90 degrees to get that. Okay, so it's like your hand. If you picture your hand, right? Imagine this solenoid as your hand. Now, this example is if your hand is flat down, like flat down literally on a table, and then North Pole on your left, South Pole on your right. Okay, and then your normal is obviously going to be perfectly vertical directly up in like this direction, if you can see my camera, right? And then in this case, it's almost as if now your hand, instead of being flat on a table, it is like it's sideways, completely sideways, like standing on its side and facing away from you directly, perfectly like vertical, basically your hand is. And then in that case, your normal line would be to the right, okay, perpendicular to the surface of your hand. Okay, so it's like you had it like this on the table, and now you just flipped it perpendicularly 90 degrees, and now it's sitting like this, like you're ready to smack someone. Okay, and then in that case, your normal line would be perpendicular to it, or facing to the right or facing to the left, depending where your surface is. But basically, you need to understand it's perpendicular to it. So if we had to consider the normal line for this guy, okay, the normal line for this would basically be in this direction. Okay, perpendicular to the surface. There's the surface. And perpendicular to the surface, you'd have the normal line. And of course, you still have the magnetic field line. Okay, and now you can see that the magnetic field lines and the normal line is in the same direction. Okay, so the angle between them is 0. They're parallel to each other. They're in the same direction. Okay, so that's important to note. Here, the normal and the magnetic field lines are perpendicular. Here they are parallel. They are in the exact same direction. Okay, so the angle between here between them is 0. So here we'd use cos 0, and here we would use cos 90. Okay, and yeah. Okay, so that's really important. So we went through this. Okay, so let's have a look at this example while we're at it. Get rid of all of this. Okay, let's have a look at this example. Okay, so this example says a rectangular wire coil with a length of 5 centimeters and a width of 2 centimeters is placed perpendicularly in a magnetic field that is 20 T in size, as in sketch A. Right? The coil is then rotated through 90 degrees over 0.5 seconds to the position in sketch B. Calculate the induced EMF. The coil consists of 100 turns. Okay, so firstly, right, induced EMF, let's take note of the formulas. Induced EMF is equal to negative N times delta phi, okay, over delta T. Now, delta phi is equal to, let's maybe move this down. Okay, delta phi is going to be equal to the magnetic flux final minus the magnetic flux initial. So the final flux minus the initial flux. Okay, so that's important for us to note. Now we can basically calculate delta, the change in magnetic flux. So change in magnetic flux is equal to final flux minus initial flux. Okay, now why do I say we can calculate that? Because we have the values for the final flux and we have the values for the initial flux. Okay, so final flux is at B, initial flux is at A. Okay, so at B, let's consider now the formula for flux, okay, is here. It's equal to B times A times cosine theta. Okay, cosine theta. Don't confuse phi and theta. Okay. Cool. So let's calculate. Let's calculate phi final. Phi final is basically at B. Where do I write? say at B, the final flux is equal to B. So B is given. Okay, B is given. They say that the place perpendicular magnetic field that has 20T in size, this is B. Okay, it is the magnetic flux density. So we have 20 times. A is the area of the conductor, okay, in meters squared, right? So here they tell us that a rectangular wire coil with a length of rectangular, so the rectangular area is equal to length times breadth, 5 centimeters and a width of 2 centimeters. We have to convert these to meters. Okay, so here we're going to say 0.05 meters, and then this is 0.02 meters. Okay, and then the area we can use, because since it's a rectangle, we can say 0.05 times 0.02, and that's the area. So B times A times cosine theta, and cosine theta. Okay, remember, what is theta? Theta is the angle between the horizontal, the angle between the normal line and the magnetic field lines. And here, this is how we determined that it was actually the normal line and the magnetic field lines were perpendicular. Okay, because the solenoid was laying flat and its normal was perfectly perpendicular, going upwards in this direction. And magnetic field lines are from left to right, therefore they're perpendicular. So the angle we use here is 90. Then we can calculate phi initial. Okay, and this stays as B stays as 20 because the strength of the magnetic field did not change. Okay, the density of the magnetic fields did not change. So it stays as 20. The area, cross-sectional area did not change, 0.05 times 0.02. Okay, times cosine. In this case, we use 0. Let's recap. Why? Because this now, instead of being parallel or perfectly flat, the solenoid is upright. Okay, and since it was upright, its normal force would be perpendicular to its surface, which would be facing to the right or to the left in like that direction in the horizontal plane. And in that case, again, the magnets did not change and they move from left to right, and the normal force is also moving to the right. So in that case, it's parallel, and in that case, we used 0. So now we can calculate the difference, delta phi. So let's calculate this. Okay, so firstly, cosine 90 is 0. So this entire thing is going to give us 0. Okay, but cosine 0 is 1. So we can do this calculation, 20 times 0.05 times 0.02, okay, times 1, and that gives us 0.02. Okay, and magnetic flux linkage, there we have its unit. So the change in magnetic flux is going to be equal to 0 minus 0.02, which is minus 0.02. And now, okay, again, I just did it in step by step just so that you can understand, but obviously you can do it all in one step, literally, right? You don't have to do it in multiple small steps. Then we have induced EMF is equal to negative. Now, N is the number of turns or coils. They tell us in the question, the coil consists of 100 turns. So negative 100 times delta phi, negative 0.02 divided by delta T. The delta T is just change in time, right? Basically, the time it takes for the time it takes for the change in magnetic flux to happen. So to move from a flat to an upright position, the solenoid took 0.5 seconds. They say the coil is then rotated through 90 degrees over 0.5 seconds. So yes, 0.5 seconds, that's the time we use. Remember, the initial time is always 0. Not always, but in most cases, the initial time is 0. So however long it took to make the change, that's going to be the change in time. Okay, then you do this calculation, you put negative 100 times negative 0.02 divided by 0.5, and you get an induced EMF of 4V volts. Okay, so here we have it. Yeah. Okay, so this is the calculation that we'll do. Let's have a look at this. Some important theory notes. Okay, theoretical aspect notes. increasing induced EMF. Okay, so you'll see these are theoretical questions which come up often, increasing the induced EMF. So the first note is if you increase the rate of change of magnetic flux, okay, remember we discussed this, increase the rate of change of magnetic flux, which is basically the faster you move the magnet, the more current, the more EMF you are going to induce. Okay, increase the rate of magnetic flux, that is to decrease the time it takes to change the flux. Okay, obviously that is to increase the speed in movement. Okay, number one. Number two is to increase the number of loops in the coil. So if you have more and more and more and more loops, you're going to get more EMF. Okay, number three is to increase the strength of the magnet. That also makes sense. Okay, and we'll go through each of these in the formula. Okay, increase the strength of the magnet. Okay, so if it's a stronger magnet with stronger magnetic field lines. Number four is to increase the surface area of the loop. Okay, make the loop a bigger loop. Okay, and it says increase the rate of flux by changing the angle from minimum to maximum. Okay, so this minimum maximum concept, let's discuss it. Right, as you can see here, we discussed when it was cosine 90. When it was cosine 90, we got 0. Okay, 0 means no flux. There's nothing touching. But when it's cosine 0, we actually got 0.2. So what they mentioned to us was actually when the normal line is perpendicular to the magnetic field lines, that is the minimum flux. Always, 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 always. I'll take a note, yeah? Okay, yes, it, yeah. Okay, change the flux by changing the angle from a minimum of 0. Okay, I'll explain why they have minimum as 0 and maximum as 90. Okay, so we obviously have a minimum as 90, but the angle that they talking about, which I think is slightly incorrect. They shouldn't be talking about theta. Okay, so do you see sometimes people refer to it as, they'll refer to this as 90 because they're actually talking about the direction of the coil. Okay, so here the coil is upright. Okay, if I had to literally just take this, get rid of all of this. Okay, now you'll be able to tell, can you see that the coil and the direction of magnetic field lines are perpendicular to one another? So this coil is upright. It's like up, up, down. It's facing upright. And then the magnetic field lines are cutting through it. So you can see like literally all of these lines. Okay, let me do a more simpler diagram actually. Okay, actually, let's do this. Okay, and let's just say we have a coil, right? So I'm going to represent it by a cylinder. Okay, let's make it a thinner. Okay, let's make it that, right? Let's just say this is the coil. Okay, 2D, this is a 2D diagram. Okay, that's important to understand. This is a 2D diagram. Okay, now let's draw my magnetic field lines. 1, 2, 3, 4, 5. So here we can see that if they were just 5, sorry. Here we can see, okay, that only, I mean, like quite a bit, like most of the solenoid is covered by these magnetic field lines, right? Most of it. And in this case, right, it's there's, me. Okay, let's just draw it separately on a different page so that we can have 2 examples. In this case, okay, what you need to notice is that the angle between the coil and magnetic field lines in this case is 90 degrees. The angle between the coil and the magnetic field line is 90 degrees. Yes, it here. The coil is upright, magnetic field line is there. However, theta, the angle between the normal and the magnetic field lines okay, what is this? Theta is equal to 0, and I'll display it now in a second. Okay, so just be careful what they refer to sometimes. In the notes, they're referring to the first one. That's why they say maximum is 90. Okay, so if we have to consider our normal, remember our normal is now in that direction. So now we can see that the normal and the magnetic field lines are parallel. Okay, so if that in that case, that's why I'm just going to write here parallel. The angle is 0 because they're parallel. So the angle between the magnetic field lines and the normal is 0. I'm just going to put here normal. Okay, now let's do the exact same thing. Okay, but let's rotate our coil. Okay, let's get rid of this. Let's take this coil. Get rid of this. Let's take this coil and let's rotate it. Okay, let's maybe make it slightly bigger. I think it can fit. Let's put it here. Or let's even put it here. Okay, so if we have to compare these two, okay, so firstly I had the coil upright, then I had the coil laying flat. If you have to compare the amount of field lines, again, please don't ever forget the amount of field lines that cuts through the coil or whatever is the magnetic flux. That's what we refer to as magnetic flux. The amount of field lines that are passing through it in this position versus the amount of field lines that are passing through it in that position. Okay, in the second position, we have literally much less. We have 1 compared to in the first position, we have 5 field lines passing through it. Okay, so that makes a big difference. We can see that here is minimum and here is maximum. Okay, minimum might not always be 0. Maybe if it's placed there, then okay, yeah, maybe then it would be 0, but it might not always be 0. But the point is that clearly that's minimum. Okay, so that's what we need to note in this case. However, if you note that the direction, the angle between the coil and the magnetic field lines is equal to 0 degrees because the coil and the magnetic field lines are perpendicular. But if we consider our normal, and see that the normal line is perpendicular to the magnetic field line. Sorry. Yeah, obviously it's perpendicular to the surface as well. That's the definition of normal line, but it's also perpendicular to the magnetic field lines. Okay, the normal line is perpendicular to the magnetic field lines. So therefore, in this case, theta is equal to 0 and it is perpendicular. So this is why this actually can get perpendicular. This is why this can actually get really confusing, because you need to pay attention to which angle is the question specifying, which angle is the questions talking about. Okay, are they talking about the angle between the coil and the magnetic field lines, or did they say that no, this is the angle between the normal and the magnetic field lines, because they are opposite. Okay, and then if you're gonna use this as theta, this is not theta. This is not theta. If you're going to use it as theta, you're going to clearly get the opposite incorrect answer. Okay, so just be careful. The one that goes inside of the formula is this one, theta, the one at the bottom. Okay, and what's nice, actually, maybe if you get rid of the confusion, is that they're opposite. So whenever the angle between whenever the angle between the coil and the magnetic field lines is 0, then the normal is 90. That just makes sense because the normal is always perpendicular to the surface. Okay, so just keep that in mind. But yeah, okay, let us end it there. And then next week we can return where we can go through the rest of the things we didn't go through, and we can go through these questions. Okay, perfect. Okay, cool. Thank you guys so much for joining. I shall see you guys next week. Jazakallah khair. Assalamu alaikum and goodbye.